Greetings and welcome to the Dr. J Vlog series. It is Monday, September 29th, 2025. On the Mondays, we talk about mathematics and statistics. And this week, the theme is genius. So I'm going to look at different mathematical geniuses briefly today. But before I start, I just want to give a quick shout out to my late mother. She passed away last year, but had she lived, she would have been 96 years young today. Happy birthday, Mom. All right, human beings have been counting for tens of thousands of years based on certain bone fragments, tally marks. We actually have evidence of counting, early human counting. And then within the last few thousand years, we have so many civilizations that have contributed to the development of mathematics as we understand it today. From the Babylonians to the Egyptians, the Greeks and Romans, the Chinese, Hindus and other Indian civilizations, and Islamic cultures, including from both Arabs and Persians, among others, all of whom have contributed incredible advances to our understanding of mathematics. So I'm only going to, the challenge is if you're going to pick 5 geniuses from mathematics, just looking at the early centuries of mathematics, it would be incredibly difficult on that basis alone. So I'm actually going to just look at only more recent mathematical geniuses, or my top 5, if you will, one from each of the last 5 centuries. That's hard enough. So for the 1600s or the 17th century, I have to go with arguably the greatest scientist of all time. Anybody know? Take a guess. Yeah, Sir Isaac Newton. Okay, born in, let me just change this up here. Born in 1642 or 1643, depending upon which calendar you're using. And then he died in 1727. So along with his contemporary Gottfried Leibniz, they each independently invented calculus, though we actually use Leibniz's notation for differential equations these days. But it's Isaac Newton's Principia that you might have heard of, and arguably one of the greatest scientific and mathematical works ever produced by a human being. What I find most remarkable about Newton, though, is the fact that his study of physics and his efforts to explain motion in the physical world required that he actually invent this new mathematics, calculus. And so I find the entire story of Newton's work and life mind-boggling, including his fascination with alchemy and religion and all sorts of non-scientific beliefs as well. But it's Newton's calculus then that laid the foundation for classical mechanics and allowed scientists to make accurate predictions about the behavior of moving objects. And so his groundbreaking work, Principia, it's there that he introduced his 3 laws of motion, which are still used today to explain the behavior of mainly visible objects in motion. Okay, so for the 1700s or the 18th century, I tip my hat to Leonard Euler, E-U-L-E-R. Move this ahead. And you can see he was born in 1707, died in 1783. He was a Swiss mathematician. He produced more mathematical proofs and original works than just about any person in history. In fact, he had pages upon pages of additional mathematics that he'd never published in his lifetime. So he's just incredibly prolific. He developed fundamental concepts in calculus and complex numbers, which includes by definition imaginary numbers, and that figures in his Euler identity, which I'll get to in a moment, but also number theory, graph theory, geometry, many of his discoveries then bear his name. But Euler also contributed enormously to our sort of contemporary language of mathematics. That is, he was the first writer to define a function and write it in that famous format that I learned as well in school, f and then in parentheses x, okay, the function of x. And he was the first to use summation notation using the Greek letter sigma, which I use as well. We all use, especially when I'm teaching my course in statistics, as I'm doing right now. And he also introduced the standard notation for trigonometric functions and much, much more. So, but what I love most about Euler is the equation that bears his name, and it's the Euler identity, which I include actually in my tagline in my email, the very, very last thing that I include. It's eloquently stated as simply E, which is an actual number. You can calculate E, and it refers to some very specific ideas, but E raised to the power of I times pi, right? You know, the number pi, plus 1 equals 0. Okay, so e raised to the power of I times pi plus 1 equals 0. It's often referred to as the most beautiful equation in mathematics, and I have a link in the description below that describes the meaning, goes through the in greater depth and detail. I was thinking about doing a video on Euler's identity, but this one does the job perfectly well, so why reinvent the proverbial wheel? Okay, so for the 1800s or 19th century, I'm going to go, or I'm going to argue the case for, boy, this was a struggle, but I'm going to go with the German Bernhard Riemann, whose life spanned only 1826 to 1866. He died of TB just a few months before his 40th birthday. So he studied under some of the most prominent mathematicians of his time, including Carl Friedrich Gauss. I almost went with Gauss, by the way. And under Gauss's guidance, Riemann developed a deep interest in number theory. And he also ended up, this was one of his primary areas, but he also ended up contributing greatly to the fields of the theories of functions, especially of complex variables. He developed the concept of the Riemann surface, which figures again later in one of the other people I'm going to mention at the very end of this video. A mathematical object that's used extensively then in studying complex analysis. He also contributed to the study of differential equations and developed the concept of the Riemann metric, an idea that forms the basis of modern differential geometry. And his work is in fact known by his name as Riemannian geometry. Okay. And he's also remembered for his Riemann hypothesis. It's one of the most important unsolved problems in all of mathematics. And so the hypothesis was first proposed back in 1859, and it concerns the distribution of prime numbers. And it has incredible implications, too, in terms of number theory and cryptography. But as of 2025, the so-called the Riemann hypothesis remains one of the most challenging problems, unsolved problems in mathematics. And so there's $1 million prize out there if you're interested in it, that's been offered by the Clay Mathematics Institute for anyone who can solve it. So go for it. All right, and then for the 1900s, the 20th century, we arguably have more contenders than ever, but at the same time, as the frontiers have been pushed back dramatically, at least in terms of mathematics, since the Renaissance, it's harder and harder to come up with completely new and revolutionary ideas, but still many people have forged new pathways, including one, Emmy Noether. So I thought about going with Sri Ramanujan, the Indian mathematician, but Emmy Noether is one of the many lesser known or unsung, I shouldn't say unsung because she did get recognition, but kind of heroes of mathematics. By the way, just for if you ever haven't seen it, do check out Hidden Figures, the film from 2016, 2017. Fascinating. But anyway, so again, she was another German. She was born in 1882, though, so just prior to the 20th century, and she died in 1935. As you can imagine, then she faced numerous challenges as a female in an obviously male-dominated field. And still, her groundbreaking contributions in terms of abstract algebra, applied mathematics, and theoretical and mathematical physics would end up revolutionizing how mathematicians and physicists would approach complex problems. And so Noether's work focused especially on algebraic structures, and she developed a range of groundbreaking mathematical concepts that challenged existing theories about the nature of algebraic equations. And her most significant contribution, though, was her formulation of the Noether theorem, which provided deep insight into the relationship between the symmetries in physical systems and the underlying laws of nature. And so if you want to do a deeper dive, I'll recommend that you read Emmy Noether's Wonderful Theorem by Dwight E. Neusenschwander. Again, her work, as I mentioned, was influential in terms of theoretical physics, and her concepts were critical actually in developing the theory of relativity and quantum mechanics. And then she also made contributions in a number of other fields, so much so that she was awarded, I should say, numerous honors throughout her lifetime, including the prestigious Ackermann-Tubner Memorial Award in 1932. She was elected to the American Academy of Arts and Sciences in 1935. And again, she continues to be a powerful inspiration to young mathematicians and scientists all over the world. And her legacy truly lives on in terms of how we think about complex mathematical problems. All right. And then finally, the 21st century, we've only had 25 years, obviously, thus far. But being married to an Iranian, I'm going to single out the late, amazing Maryam Mirzakhani. This is the Iranian genius who only, again, had 40 years on the planet from 1977 to 2017. And she was a professor ultimately at Stanford. But she, unfortunately, she died from breast cancer that had metastasized to her bones and so on in 2017. So she was born originally, though, in Tehran in 1977. And then in 1994, she became the first Iranian woman to win a gold medal at the International Mathematics Olympiad in Hong Kong. And she scored a 41 out of a possible 42 points. And then the next year in Toronto, she became the first Iranian to achieve the full score and win 2 gold medals in the International Mathematical Olympiad. Shame I wasn't following her back then. I didn't know about her. I was actually living in Toronto at that time. But again, even more so, what's incredible about her is that she became ultimately the first female recipient of the Fields Medal in mathematics. And that's the kind of the mathematical equivalence, if you will, of the Nobel Prize, but in some ways even harder to win. Oh, and she wasn't just the first woman. She was also the first Iranian and the first Muslim to win the Fields Medal. And her work is far beyond my puny comprehension, but she mainly worked in an area and made groundbreaking discoveries in hyperbolic geometry, the spherical Riemann surfaces. Remember Riemann that I mentioned earlier. And these differ dramatically from the kinds of surfaces that we mostly encounter in everyday life. And so she figured out these unique formulae for predicting the probability of forming closed loops on these complex geodesic surfaces. So that much I understand. But her creative mind was just remarkable. She was able to bridge algebra and geometry and number theory, and she was able to solve these incredibly complex problems that actually have a number of real-world applications when we think about complex systems. And everything from the most efficient ways to paint a surface to cryptography to the possible origins of the universe. People are using some of her work in that regard. And so again, I'm going to include just a short link below so you can listen to her own voice and listen to her talk about her early life briefly, and then her main interest in mathematics. And it's such a bittersweet remembrance of another genius taken from us all too soon. But maybe her daughter has that same genius. Her daughter would be a teenager these days. I don't know what she's up to, but who knows. All right, as ever, I hope you enjoyed this. May you and yours continue to create peace in your lives, nurture love in your hearts, and dole out hugs in abundance, and appreciate genius wherever you may see it in this world. We'll see you tomorrow.